Have you ever heard of sine and cosine functions? If you have, do you actually understand what they mean behind the formulas? Let's talk about that today. You see, many real-life physical phenomena naturally produce sine and cosine waves. That's exactly why these functions were created mathematically, to describe those very patterns. And one of the simplest, most elegant examples of all is uniform circular motion. So, to understand this concept, let's look at a circular road with a car moving along it. Now, one important thing to note is that this circle has a radius of exactly 1 unit. You will understand why shortly. As the car moves, we can track its position by projecting it in 2 perpendicular directions, horizontally and vertically. We measure this position relative to the center of the circle. Alright, let's start the drive. At the starting point, the car hasn't covered any angle yet, which means it is at 0 degrees. At this exact moment, the car is at its maximum horizontal displacement of +1, while its vertical displacement is exactly 0. As the car moves forward and covers exactly 90 degrees, its horizontal displacement drops to 0, and its vertical displacement reaches its maximum of +1. When the car reaches 180 degrees, its horizontal displacement is at its maximum in the negative direction, which is -1, and its vertical displacement returns to 0. At 270 degrees, the horizontal displacement is 0, and the vertical displacement reaches its maximum in the negative direction, which is -1. Finally, at 360 degrees, the car completes the loop and is back exactly where it started. Its horizontal displacement is +1, and its vertical displacement is 0. Now, notice a pattern here. After one complete rotation, the car returns to its starting position with the exact same displacement values. As it keeps driving, every single position along the path is acquired repeatedly. In physics, when an object returns to the same positions at regular intervals of time, we call it periodic motion. Now, let's look closely at the moving car and its horizontal and vertical projections. If we simply connect the car to the center of the circle, we instantly see a right-angled triangle. In this triangle, the line from the center to the car is always the hypotenuse, while the horizontal and vertical projections form the other 2 perpendicular sides. This means we can directly apply the classic definitions of sine and cosine. Now, here is the real reason we chose a unit circle. Because the hypotenuse is 1. And when the hypotenuse is 1, dividing by it changes nothing. So, vertical displacement directly becomes sine theta. Horizontal displacement directly becomes cos theta. The displacement itself is the sine and cosine value. This is exactly why the unit circle was chosen, to make the hypotenuse 1. So that sine and cosine values directly represent real, physical displacements of the car. This is pure geometry, behaving exactly as it should in reality. Amazing, right? Okay, now let's step back from the circular track for a moment and look at things from a purely mathematical side. What exactly is a function? And why do we call these the sine and cosine functions? Think of a mathematical function like a specialized machine. You put an input into the machine, it performs one specific operation, and it spits out an output. The machine is always named after the exact operation it performs. The purest form of the sine function is simply written as: it takes an angle theta, applies the sine operation, and gives you y. That's it. Since sine is the only operation happening here, we call it the sine function. Similarly, the purest form of the cosine function is written as: same idea. It takes angle theta, applies cosine, and gives you y. Since cosine is the only operation, we call it the cosine function. You might see sine and cosine functions on a unit circle, as a wave, in equations, or as an infinite series. But all of these are just different ways of showing the same simple idea. The function always gives you a displacement length for an angle. Now, remember where we left off. In our unit circle, the vertical displacement of the car was exactly sine theta, and the horizontal displacement was exactly cosine theta. This means the circular motion of a unit circle is not just producing displacements, it is naturally producing the sine and cosine functions themselves. Now, one small but important point, in the cosine function we wrote y equals cos theta. So how are we gonna use this function for horizontal displacement, which is simply denoted by x? Don't get confused here. Whether you write x, y, or any other letter, it doesn't matter. That letter is just a label for the displacement value. The function itself does not change. Now, what if we plot these two displacements on a graph against time? Let's see. Don't be confused why we wrote t or theta. They are both perfectly locked together. I mean, as time increases, angle increases, right? That's why we can write either t or angle. One more thing before moving on, horizontal displacement naturally moves left and right in reality. But on the graph, we are representing it also in the vertical direction. This might feel contradictory, but it does not affect reality at all. We are not changing what horizontal displacement is. We are simply plotting its value against time in a convenient way. The graph doesn't care about direction, it only cares about how the value changes over time. Now, let's look at the graphs we just created. The continuous waveform generated by plotting the output of the sine function over time is defined as a sine wave. Similarly, the waveform generated by plotting the output of the cosine function is defined as a cosine wave. In short, we name these physical waveforms after the specific mathematical functions that dictate their geometric shape and behavior on a graph. But do you know how they are actually formed? I mean, why do they even follow such a waveform? To understand this, we have to analyze the displacement values for every single angular position that we discussed at the beginning of the video. Let's revise them again. Now, if we plot these displacement values against the angle, we will get exactly these waveforms. But remember, the sine and cosine waves have slightly different waveforms if we compare one complete cycle from both, that is, from 0 to 360 degrees. The sine wave starts and ends with zero displacement, whereas the cosine wave starts and ends with maximum displacement. Now, let's look at something interesting. Do you see any pattern between the displacement values given by sine and cosine operations on every angle? If not, let's look at the table we made earlier again. Now, it clearly shows that the cosine operation on any angle produces a certain value. If we move 90 degrees ahead of that same angle and apply the sine operation, we get the exact same value. That means cosine produces the same value 90 degrees earlier than sine. This is why we say sine lags behind cosine by 90 degrees. We can write this mathematically as, or equivalently. We can also verify this on the graph. When both waves are plotted together, the sine wave appears visually ahead of the cosine wave. Some might conclude that sine produces values before cosine, but that would be a mistake. Both waves are moving along the time axis. And on this graph, moving to the right means moving forward in time, meaning later, not earlier. The sine wave has the same shape as the cosine wave, but it sits further to the right, which means it occurs later in time. So, despite appearing visually ahead, sine is actually behind cosine in time. Cosine reaches the same values 90 degrees earlier than sine. Therefore, cosine is ahead, not sine. Well, that's all for today. See you next time.